This video is on Section 4.3, which is about irreducibility and unique factorization in polynomial rings. Here, as in the previous section, we'll see how polynomials over a field are very similar to the integers. Before we can talk about unique factorization, we need some terminology. Here and always, we let capital F denote a field. We say that two polynomials, f of x and g of x, in our polynomial ring with coefficients in capital F are associates if f of x is a constant multiple of g of x, where that constant c is non-zero. For example, if we look at the polynomial f of x being 3x to the fifth minus 4x squared plus 1 in the polynomial ring with coefficients in Z5, we can find a monic associate of f of x by multiplying f of x by 2. If we do that, we see that 2 times f of x is just x to the fifth plus 2x squared plus 2. Here we have to remember that all of our arithmetic in coefficients is occurring over Z5. So when I take this 2, for instance, and multiply it by the leading coefficient 3 in the original polynomial, I get 2 times 3, which is 1 in Z5. A few facts, or a couple of facts, about associates. The first is that every non-zero polynomial in our polynomial ring has a unique monic associate. We can obtain that unique monic associate just by multiplying f by the multiplicative inverse of its leading coefficient, just like we did in the previous example. Here, little f of x has a leading coefficient of 3, and we just took that polynomial f of x and multiplied by 2, which is the multiplicative inverse of 3 in Z5. Second, if you have a polynomial in the polynomial ring over Zp, where p is prime, that polynomial will have p minus 1 associates, and the reason for that is that there are p minus 1 non-zero constants in Zp. Next, we introduce the idea of irreducibility for polynomials. We begin by noticing that any polynomial is divisible by its associates and by any non-zero constant. And it may be divisible by other things. We don't know. But a non-constant polynomial p of x is said to be irreducible if its only divisors are its associates and the set of units. That is, the non-zero constants in our base field, capital F. If you have a non-constant polynomial that's not irreducible, then that polynomial is said to be reducible. We illustrate this concept of irreducibility with an example. We're going to have this polynomial, or little f of x, equaling 3x plus 1, and we're going to look at that polynomial in the polynomial ring, say, Z5, join x. It's always important whenever you're working with polynomials to make note of the field capital F of coefficients, because all sorts of things with polynomials depend on what that base field is. You know, all of the computations you do with coefficients, in fact, whether a polynomial is irreducible or not, can depend on what the base field is. So we always want to be mindful of our setting when we're working with polynomials. All right, well, we want to show 3x plus 1 is irreducible in this polynomial ring. So we start with a divisor, g of x, a polynomial that divides evenly into 3x plus 1. If it divides evenly into 3x plus 1, then we can write 3x plus 1 as g of x times h of x for some other polynomial in this polynomial ring. And then if we look at the degrees of these polynomials, because the degree of 3x plus 1 is equal to 1, that forces the degree of g to be 0, or the degree of g to be 1. If the degree of g is 0, then we know that g is a non-zero constant polynomial. On the other hand, if the degree of g is 1, then the degree of h has to be 0. That's according to theorem 4.2, essentially. And that makes h of x a non-zero constant polynomial, and therefore g is an associate of f, right? So how do we see that g is an associate of f? Well, if h of x is constant, then we have g of x times c equals f of x. And that means that g of x is equal to c inverse times f of x. And so g indeed is a non-zero constant multiple of f, which makes g an associate of f. Okay, well, those are the only possibilities. Therefore, the only divisors of f are the non-zero constants and the associates of f, and that makes f irreducible. If someone drives up and hands us a polynomial, how do we tell if it's irreducible? Well, it looks complicated, perhaps, and in fact, it's often a hard question. And one of the things that we're going to be wanting to do as we proceed through Chapter 4 is try to answer that question in certain special settings. This next result, Theorem 4.11, is sort of a beginning towards answering that question. Here in this theorem, what we want to do is recast the idea of reducibility in terms that perhaps you are more familiar with from K-12 mathematics. So this theorem says that if we start with a non-zero polynomial, we say we will know it's reducible if and only if there are polynomials g of x and h of x that multiply together to give f of x, and whose degrees are both strictly smaller than the degree of f of x. Again, that's probably more in keeping with the way that you have thought about, say, reducible polynomials in the past. Right, now we're going to redo the previous example using this theorem. So you might remember that in the previous example we had this polynomial 3x plus 1 in the polynomial ring Z5 adjoin x. So if 3x plus 1 were reducible, then we could write it as a product g of x times h of x, where both g and h would have degrees that are strictly smaller than the degree of 3x plus 1. But the degree of 3x plus 1 is 1, and that would force the degree of g to be 0 and the degree of h to be 0. But we know that can't happen because if we multiply g and h together and they both have degree 0, then the degree of the product would be the sum of the degrees of the original polynomials, and that would force the degree of 3x plus 1 to be 0, which we know is false. And therefore, we've argued, according to Theorem 4.11, that 3x plus 1 cannot be reducible, and therefore it is irreducible. Okay, there are strong parallels between the notion of irreducibility in a polynomial ring over a field and the notion of primality for integers. So here at the top, I've just reminded you of what it means for a polynomial to be irreducible in a polynomial ring over a field. And now what we want to do is compare this notion to primality in the integers. So you can think of the units in our polynomial ring, namely just the non-zero constants in the polynomial ring, as being like plus and minus 1 in the integers. If you look at the integers, the only units in the integers are plus and minus 1, whereas the units in our polynomial ring are our non-zero constants. Now, if we look at associates of a polynomial in our polynomial ring, how do we get those? Well, we multiply our polynomial by any non-zero constant. That is, we multiply our polynomial by a unit in our polynomial ring. Well, over in the integers, we can think about starting with a number p, and if we multiply it by the units in the integers, we're just multiplying by plus or minus 1, and so the associates of p in the integers are just plus and minus p. Now we have this phrase that occurs in the definition of irreducibility that says the only divisors of p of x are its units and its associates. Now if we translate that to the world of integers, that's like saying the only divisors of the number p in the integers are the units plus and minus 1 and the associates plus and minus p. Now here you might notice that in the definition of irreducibility we require our polynomial to be non-constant. In other words, we require it to be not equal to the zero polynomial, and we don't want it to be a non-zero constant polynomial either. So if we translate that to the world of integers, we are then sort of requiring that this special number be non-zero and that it not be a unit, that is, not be plus or minus 1. So if we consider these previous 4 bullet points that we just discussed, we can therefore think about an irreducible polynomial in a polynomial ring as being very much playing the role that a prime number does within the integers. If irreducible polynomials are going to play the same role in polynomial rings that prime numbers play in the integers, then we expect some sort of analog of the fundamental theorem of arithmetic to be true for polynomials. Indeed, this is the case, and in order to get to that theorem, we need a preliminary theorem, this theorem 4.12 from your book. So we start with capital F being a field, as always, and we have a p of x being a non-constant polynomial in the polynomial ring with coefficients in our field capital F. The following statements are equivalent. First is the statement that p of x is irreducible. Second is the statement that if p of x divides a product of polynomials, then p must divide evenly into at least one of those polynomials. And then finally, if p of x is a product of polynomials, then one of those polynomials must be a non-zero constant polynomial. So remember that these statements being equivalent means that if one of the statements is true, they're all true, and if one of the statements is false, they're all false. Here we have the fundamental theorem of arithmetic for polynomials. It says that every non-constant polynomial in our polynomial ring over a field can be written as a product of irreducible polynomials. And further, this factorization is unique in the sense that if we start with a non-constant polynomial f of x, and we write it, say, in two ways as products of irreducibles, where here in this second product, the single dot should be replaced by triple dots. Anyway, if we have these two representations of f of x as products of irreducibles, then there are the same number of irreducibles in each factorization. And in fact, after you reorder or relabel, the q sub i's must be associates of the p sub i's. Now, there are two parts of the proof of this theorem. One is to prove the existence of a factorization, and the second part is to prove uniqueness. You may remember when we proved this theorem for integers, we proved the uniqueness part in class, and I had you read the existence part. Here, in this proof for polynomials, we're going to do the opposite. We're going to prove the existence part, and I'll have you read the uniqueness part. Now, when you're reading the proof of FTA for polynomials, it might be a good idea for you to skip back and also look and remind yourself of the proof of FTA for integers. And when you do that, you should notice how very similar the proofs are. That is, the proof for polynomials is very similar to the proof of FTA for integers. Okay, on to the existence proof. We're going to begin with a set, capital T. That T is going to represent all of the non-constant polynomials that are not products of irreducibles. And our goal ultimately is to show that this capital T is an empty set, meaning that every non-constant polynomial will be a product of irreducibles. Now we have this auxiliary set, S, that goes along with capital T, and it's going to be the degrees, the set of degrees of all the polynomials that live in T. And we notice that S must be a subset of the positive integers. Now, for a contradiction, we're going to suppose that this capital T is non-empty. Now, if T is non-empty, then S must be a non-empty subset of the positive integers, and therefore it must have a smallest element by the well-ordering axiom. We'll let n denote that smallest element of S. And we're going to select a polynomial f of x in T whose degree is equal to n, this smallest element of S. Now, remember that things in T are not products of irreducibles, and we'll count a single irreducible as being a product of irreducibles. And that means that f of x itself is not irreducible. And that means by theorem 4.11, we should be able to write f as a product of two polynomials, g and h, where the degree of g and the degree of h are both strictly less than the degree of f. But that would mean that g of x and h of x are not members of T because their degrees are both smaller than n, which is the smallest degree that's allowable for elements in capital T. So g and h are non-constant and they are not in T. So each of g and h are products of irreducibles. So then if you multiply g and h together to get f, you then get f as a product of irreducibles, and this contradicts the fact that f is a member of T. And that finishes the existence proof. The notion of associate and irreducibility can be extended to any integral domain. In fact, on a previous slide, I attempted to indicate how these ideas translate to the integers. You might remember that the associates of a number were just plus and minus that number, and irreducibles in the integers are just the primes. Now, while these notions of associate and irreducibility can be extended to any integral domain, the existence of a theorem like the fundamental theorem of arithmetic does not exist in every integral domain. However, those special domains that do have an analog of FTA are called unique factorization domains. So both the integers and polynomials over a ring are UFDs. But this domain, where z adjoin the square root of -5, so numbers in there are of the form a plus b times the root of -5, where a and b are integers, that domain is not a UFD. In fact, if we take the number 6, we can write it as a product 2 times 3 of irreducibles in this ring. We can also write it as a product here, 1 minus root of -5 times 1 plus root of -5. That is also a product of irreducibles. And none of these objects, 2, 3, 1 minus root of -5, and 1 plus root of -5, none of them are associates of each other. So FTA fails in this particular ring. Now, one thing that helps the integers and the polynomials to be UFDs is that both of those rings have a division algorithm. Now, any domain that has an analog of the division algorithm is called a Euclidean domain. And there's a theorem in algebra that says any Euclidean domain is automatically a unique factorization domain. So unique factorization can be a powerful tool for proving certain things. For instance, let's just briefly take a look at this scenario. Let's suppose we have a complex number that is an nth root of unity, meaning if you take a to the nth power, you wind up with 1 again. And further, let's suppose we have 3 non-zero integers x, y, and z, where z to the n is x to the n plus y to the n. We can take x to the n plus y to the n and factor it into a product of these binomials that involve the nth root of unity, a. Now, it turns out that that factorization could be used to give just a brilliant proof, short proof, of Fermat's last theorem if you always knew that you had unique factorization in this ring Z adjoin A, where A is the nth root of unity that we talked about a little bit earlier. But it turns out that you don't always have unique factorization in this ring, and so this beautiful idea that we might have for proving Fermat's last theorem goes out the window. In fact, this method was proposed in 1847 by a guy named Gabriel Lamé, who presented this argument to the Paris Academy of Sciences, and it was shot down a little bit later when other mathematicians like Liouville pointed out that Lamé's argument required unique factorization and that it was not certain to occur. Okay, well, anyway, perhaps that's enough of that, and so this is the end.